All right, welcome to lecture 3. I've entitled this The Introduction to Linear Algebra. Hopefully it's going to give you enough of a foundation to sort of see where some of these quantum properties come out of the math. Certainly linear algebra is an entire field into itself, and you can take entire semester or year-long courses in it. So I'm going to do my best to at least give you a flavor of what the important aspects are with relation to quantum mechanics in the next hour and a half or so. So this lecture, since it's basically a math lecture, is going to be very text heavy. I tried my best to add pictures, but there's only so much you can do. Next week, we'll be back to more experimental stuff, which is really what I enjoy more. After that, we'll have another theory lecture, and then we'll have a final experimental lecture after that. All right, so we're going to start with sort of a graphical review of some properties of vectors, and then we're going to get into linear algebra, matrices, and things like that. And then I'm finally going to try to tie it back to quantum mechanics. So briefly, a review of some of the properties of a vector. Usually the picture we start with when we talk about vectors is an arrow. It has a direction and it has a magnitude. We can write arrows with where their endpoint is. Starting from 0, 0, it can go to coordinates 4, 3, if we're working in just two-dimensional space, x, y plane. And it has a certain length, and that's the magnitude. We can think of vectors as forces. Lots of things could be bundled as vectors, but mathematically, they're just this abstract thing with magnitudes and directions. And we can say if all we care about is the direction and the magnitude, then we can actually translate the vector around and still retain all its properties. Really, where we have the starting point is a little bit arbitrary. Where do you set 0, 0? It's a little bit arbitrary. So we can retain a lot of the properties of the vector and just translate it in space to different positions. An important property of vectors is that we can decompose them into vector components. So we could decompose this red vector into the x component and the y component. The x and y component need to be orthogonal for this to work. And the magnitude of the vector can then be calculated from its coordinates. Here we're translating the green y vector in space, but still retaining its properties. And so now we can make this 3, 4, 5 right triangle and do the Pythagorean theorem, 3 squared plus 4 squared equals 5 squared. So this being allowed to translate vectors in space lets us do some graphical calculations. It lets us think about things geometrically, at least in the dimensions we can wrap our heads around. So my head can wrap around 2 dimensions, it can wrap around 3 dimensions. Once you get beyond 3 dimensions, it gets really fuzzy. It's just hard to think in a 10-dimensional space, but certainly vectors exist in 10-dimensional spaces, and we're going to start with these sort of graphical ideas to get people, geometric graphical arguments to get people sort of up to speed, and then we'll switch to more abstract. Things will get more abstract as the talk goes on. If you get lost, please speak up. If you are lost early, then you will be even lost. You will be even more lost later. All right. So we can add addition. We can add vectors together. Vector addition can be done algebraically, just adding the coordinates. Vector 1 with coordinates x1, y1 plus vector 2 with coordinates x2, y2 would sum up to a vector with coordinates x1 plus x2 and y1 plus y2. We could also do it geometrically. This is that head to tail idea of adding vectors. So again, we're just translating the vector in space that we're adding. And if we line them up head to tail, and so we have our first vector plus our second vector, and then we can draw the resultant addition, the result resulting vector from the initial point to the end point, the tail of the first vector to the head of the second vector. So that's a nice geometric graphical representation of that. We can subtract vectors, doing head-to-head, and then translating back sort of the inverse process. We can do scalar multiplication of vectors. If we have our vector, our green vector x1, y1, we multiply it by some scalar c. A scalar is just a number, remember? So if we multiply it if we let c equals 2, we go from the vector being 2, 2 to the vector being 4, 4. And if we're doing it algebraically, we just multiply c times the x coordinate and c times the y coordinate. If we have a negative sign, if c is a scalar with a negative sign, it's going to flip the direction of the vector, but it's still a valid mathematical process. We still are scaling our vector by this numerical value. There's a couple different ways you can multiply vectors together. One of them is called the dot product, which is a scalar product. So we get a number as an answer. We don't get another vector, we get a number. So if we do a dot b, the mathematical formula is x1, x2 plus y1, y2. And then we have the magnitude of a and the magnitude of b, and times cosine theta, which is the angle in between the two vectors. A useful property of the dot product is that it equals 0 for orthogonal vectors. We need to check if vectors are orthogonal because that makes them linearly independent. If they're not orthogonal, then they are linearly dependent. If we want to solve a system of linear equations, we need 3 unknowns and 3 linearly independent equations. If they're not linearly independent, then we can't fully solve our system. So having this dot product and checking that it equals 0, and it equals 0 because the cosine of 90 is 0, is a very useful way to check what's going on in our system and make sure that we have linearly independent vectors. When we have just 2 dimensions, we have x and y. If this is a vector purely along x and this is a vector purely on y, there's no way I can express the purple vector as some part of the green vector. They are completely independent, and it's easy to see graphically in lower dimensions. In higher dimensions, it gets very hard to think about, to see. So that's why doing this formula of the dot product and checking if it's 0 is a really powerful tool for checking for orthogonality. So orthogonal vectors are linearly independent, and making sure things are linear equations or vectors are linearly independent ends up being important in quantum mechanics. So vectors can be said to span a space. If we just think of the XYZ unit vectors, they're the standard ones that we use to span 3-dimensional space. To span space, the vectors must be orthogonal. And once they're orthogonal, we say that forms a basis set for the space we're working in. So I had pictures of 2 dimensions, here's 3 dimensions. We can have higher dimensional spaces. It's just very hard to draw. And the choice of the basis set is arbitrary. Again, where do we set 0? It's a little arbitrary. Where do we define 0 as? So I drew these vectors A, B, C, and they still form a basis set of the vector. They still form a basis set and span this vector space because they're orthogonal to each other. The only requirement is you need the same number of vectors as the dimension space that you have. So if we're working in 3 dimensions, we need 3 orthogonal vectors. If we're working in 4 dimensions, we need 4 orthogonal vectors. If we're working in 10 dimensions, we need 10 orthogonal vectors. My head can't work fit itself around what 10 orthogonal vectors would look like. So I can't even begin to try to draw it, but the math, you just do the same process with the math and it's fine. And you shouldn't be so scared or it shouldn't be so unfamiliar of changing basis sets. We change coordinate systems when we solve physics problems fairly often. So we can go from Cartesian coordinates, x, y, z, to spherical coordinates, r, theta, phi. And the r, theta, phi vectors are just a different basis set. It's still a three-dimensional space. We have three orthogonal vectors. It's a different basis set to describe this space. And you want to describe the space with a basis set that makes sense for the data you're trying to use, the data you're trying to describe. So sometimes we work in spherical coordinates because it describes the data that we're working with much better than the Cartesian XYZ coordinates. Another way to multiply vectors is called the cross product. So with the cross product, your answer is a vector. And if we have two vectors, and now we're going to write them mathematically in a bit of an abstract form. So we have vector u is a1i plus a2j plus a3k. And vector v is b1i plus b2j plus b3k. U cross v is going to be described by this longer equation. And the vector u cross v is orthogonal to u and v. So if we need to generate a new vector that we know is orthogonal to two other vectors, then we can use the cross product and this automatically generates the third orthogonal vector. You can think of this as if you've taken electricity and magnetism, the right-hand rule, u cross v, electric field cross magnetic field is direction. But the important thing here is that it gives us a vector as an answer rather than a scalar as an answer. And then the vector that it gives us is by definition orthogonal to the first two vectors. And we end up with a vector as the answer. There's also what's called the triple product, which is the absolute value of u dot v cross w. And it represents the volume of this space that's formed by these vectors. So it gets progressively interesting as you try to multiply different things together. So let's move into trying to solve a set of linear equations. Excuse me. So linear algebra deals with linear equations. What does it mean to be a set of linear equations? So a set of linear equations is linear, so it has no powers. It's not x squared, y cubed. It's linear in the coordinate systems that we're working with. X, y, z are all linear relations. So we can have a set of equations, three unknowns. We can start to try to solve that. But in general, linear equations are a1 x1 plus a2 x2 plus dot 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 an xn equals b, as long as ai and b are scalars. As long as they're just numbers, then we have a linear equation. So we have three unknowns, three equations, and we're going to start solving by Gaussian elimination. So Gaussian elimination is this process of trying to manipulate the equations so you get the three different variables in different lines as you manipulate them. And as you isolate the different variables, you suddenly get the values for it. So we'll start with this example of the three equations. And if we subtract 3 times the first equation from the second equation, so if we multiply the first equation by 3 and subtract it from the second equation, we'll eliminate x. So x has now been dropped out of the second equation. So we're systematically trying to eliminate the variables from the different equations so we can isolate the variables and solve for their values. If we continue and take our new set of equations and subtract 2 times the first equation from the third equation, we can eliminate x from the third equation. And of course, all these steps are reversible. We can just go back the other way. And so we're not changing anything fundamental about the system that these equations describe. We're just trying to isolate the variables so we can wrap our heads around what's going on and find values for it in a systematic way. If we keep going to eliminate variables, we can subtract 2 times the second equation from 5 times the third equation. And now we've gotten z isolated by itself. So 3z equals 6, we can easily solve z equals 2. And now we can back substitute, put our value of 2 in for the second equation. So negative 5y plus 2 equals negative 3. So therefore y equals 1. And then if we back substitute again, put our y equals 1 and z equals 2, we can solve and find x equals negative 3. This is clearly a lot of writing. It's not the most elegant way to express all this. So we're going to switch to matrix notation. And matrices are really the heart of linear algebra. Manipulating matrices is the heart of linear algebra. But I wanted to set up something a little more familiar, just trying to solve 3 equations with 3 unknowns and sort of algebra 2 type thing to get people up to speed and comfortable where we're going. So if we start with the same set of equations, writing this x, this y, and this z over and over again gets tedious fairly quickly. So we're going to take those as red, and we're just going to have take the coefficients, and we'll have our x column, our y column, and our z column. And then I put a little line just to denote that these are the variables, and this is the scalar, the answer on the other side of the equal sign. So I'm just taking all these coefficients and writing them out in a matrix, and the x and the y and the z are all taken as understood at this point. So then we can go through the same series of manipulations. We subtract 3 times the first row from the second row. Here we've zeroed out the x in the second row again. We can subtract 2 times the first row into the third row. Here we've zeroed out the x in the third row. We subtract 2 times the second row from 5 times the third row. Now we've zeroed out the y in the third row. And then we're again back to this 3z equals 6. But the interesting thing about the matrix side of it now is that we've suddenly have a diagonal and we have zeros below the diagonal. So when you're dealing with matrices, if you can rearrange the matrix into something that has all zeros below the diagonal, that's called echelon form. And echelon form is a very useful way of starting to represent your vectors. All right, so we can push on with our back substitution. We can divide the third row by 3. So now we have z equals 2. We can subtract row 3 from row 2. And then divide both sides by negative 5. And so now we have y equals 1. And then we can subtract the third row from the first row. And subtract twice the second row from the first row. And now we end up with something even more interesting. We've got a diagonal matrix. We only have values on the diagonal. And in fact, all these ones, all the values on the diagonal are 1s, which in fact makes it what's called the identity matrix. So with the identity matrix, you can very easily read off values, x equals -3, y equals 1, z equals 2. But often when we're doing linear algebra, we're trying to diagonalize the matrix, get to a spot where it's easy to understand what the data is telling us, clean up all this superfluous values and get down to just what the pure essence of the matrix is. All right, so clearly matrix notation is a very useful way to start thinking about vectors. If we go back to our dot product and we just have our u and v vectors, and we drop the x, y, z. Now I have a 4-dimensional vector, so we can call it ijkl maybe. But let's just drop those and just keep the coefficients. To do the dot product, and remember before we had the dot product had that cosine theta in it. Now it's really hard for me to think in 4 dimensions and figure out where that cosine theta would be and what the theta would be. So there's another way to do the dot product. In matrix notation, we transpose one of the matrices, one of the vectors, so it's vertical. So we have a horizontal times a vertical, and we multiply the first elements together. So 1 times 6, and then we add the product of the second 2 elements, so -2 times 7. Then we add the third element, the product of the third elements, 3 times 1. And we add the product of the fourth element, -4 times -2. And we get our scalar, it's 3. So u and v in this case are not orthogonal. They're not linearly independent because the dot product came out as a real value and not as 0. If u and v were orthogonal, if they were linearly independent, then this dot product would be 0. So now we can extrapolate to higher dimensionalities and don't have to try to think of what the cosine theta between these 4-dimensional vectors is. So that's a useful way, and it's a useful way to check if 2 vectors are independent, if they're orthogonal. And remember, we always end up with a scalar as the answer in a dot product. So if you end up with a vector, you've done something off. There's a property of a matrix called the determinant. Each square matrix has this special scalar called the determinant that's associated with it. The determinant of the matrix is often denoted by det of A, or sometimes just what looks like absolute value of A. So if we have a two-dimensional matrix, a 2x2 matrix, the determinant is calculated by going diagonally A11 times A22 minus A12 times A21. And a system of linear equations will have a unique solution if and only if the determinant is non-zero. So now we don't have to solve pages and pages of math and figure out that a system of linear equations doesn't have a unique solution. We can just take the determinant and that will tell us if it has a unique solution or not. So for a 2x2 matrix, there's sort of a cleaner way to visualize it. A 3x3 matrix gets a little messier, and then higher order matrices get even messier. Granted, you very rarely do these things by hand anymore. Computers are very good at handling matrices and calculating these things for you. You can see it's a very repetitive process, so computers are good at it, whereas humans are lousy at tedious, repetitive things. So, but understanding sort of where things come from is worthwhile. So a determinant of a 3x3 matrix, if we have A11 to A33, we start by blocking out the first row and the first column, and we take A11 and then we multiply it by the determinant of the remaining, by the determinant of the remaining matrix. So here we have A22 times A33 minus A23 times A32. We repeat this, we block out the second row and column. So then we have A22 times the determinant of the remaining matrix. And then we block out the third row and column, and we have A33 times the determinant of the remaining matrix, so that the determinant of A is equal to this long thing all put together. You have to remember to alternate your signs. This has to do with even and odd functions. So the first one is positive, the second one is negative, the third one is positive. If you had higher orders, it would go negative, positive, negative, positive. And remember, at the end of all this, you should just get a scalar, just get a number. All right. So then we can go back to our cross product and again write it as vectors u cross v, but now we can just have it in determinant notation. So it's the determinant of A2, A3, B2, B3 times I, the determinant of A1, B3, A1, A3, B1, B3 times J, plus the determinant of A1, A2, B1, B2 times K. So this becomes just a cleaner way to start representing the cross products and multiplying things. So the matrix notation is powerful, and it just cleans things up and makes it a lot easier to read. Now we're going to talk for a moment about multiplying a matrix times a vector. So if you multiply a matrix times a vector, the answer is a vector again. The dimensions of the matrix and the vector have to match and able to be able to multiply them together. And you'll see why in a moment. So the process for multiplying a matrix times a vector is we multiply the first two elements together. So A times X becomes AX. And then we add the next two elements, B times Y. So AX plus BY is our first element in our resulting vector. And then we move to the next line. C times X plus D times Y is the second element in the resulting vector. So we've gone from a matrix and we've reduced it in dimensions, multiply a 2 by 2 matrix by a vector, and then we get just two elements in the resulting vector. All right. So now we're going to build up to the idea of eigenvectors and eigenvalues, which are important when we get to quantum mechanics, and they came out of the study of linear algebra. So I'm going to have sort of a silly example to get us away from the physics for a moment so we can just look at the math. And then we'll come back after we've sort of got our heads wrapped around the mathematical concepts and talk about the physics again. All right, so I have a hypothetical city called Big City, and it has two newspapers, the Big City Times and the Big City Herald. So the Times has 38% market share and the Herald has 62% market share. And every year, 10% of the Times readers get frustrated and switch to the Herald, but 7% of the Herald's readers get frustrated with the Herald and switch to the Times. And if we assume newspaper readership stays constant, what is this long-term outlook for the Big City Times? So it's a really silly problem, but I chose this to get us out so we don't worry about the physics and we just focus on the math for a moment. All right, so we have 100 readers, just to make the numbers easy. 38 read the Big City Times and 62 read the Big City Herald. And after 1 year, we can write an equation. So we have 90% 0.9 times 38. So 90% readers stay with the Times. And then we gain 7% of the Herald readers. So 0.07 times 62, this equals 38.54 readers. Please ignore the fractional readership issue. It's a silly example problem. And after 1 year, we can write an equation for the Herald readership. So it's 10% of the Times readership plus 93% of the Herald readership is 61.46 readers. So yes, fractional readers don't exist, but this is a math problem, not a real life problem. Now we could take that set of equations and we could write it as a matrix and a vector. So we could take these coefficients, the 0.9, 0.07, 0.1, 0.93, and we can write it in a matrix like this. And we could take our initial readership, 38 for the Big City Times and 62 for the Herald, and we can write that in a vector. And then we could write our results as a vector too. So let's think of these vectors that we've written as state vectors. Here, the state we're worrying about is the number of readers. And so this 38 and 62 vector is the readership in the first year. This 38.54 and 61.46 is the state of the readership in the second year. So we can generalize this just being state vectors. And then we can call this matrix that we wrote a transition matrix. So this matrix transitions our system from the first state to the second state. So we have our transition matrix, we multiply it by a vector, and we have our transition matrix, we multiply it by a state vector, and then we get our new state vector. So this is a fairly powerful idea, and you can start to see how we could generalize this to more interesting problems than newspaper readership. But let's push on a little bit on the newspaper readership question. So how do we get the readership in year 3? We take our transition matrix, and we multiply it by the year 2 state vector, and this results in our year 3 state vector. And we can do this on and on, multiplying our transition matrix times the state vector to get our next state vector. And I went ahead and multiplied it out through year 7 for you. So our state vector in year 7 is 40.14 and 59.86. You can see that the change is slowing, and so eventually this system should reach a steady state. So if we take the transition matrix P times the state vector X, we'll eventually get an equation that is P times X equals X. When we hit steady state, we'll get the same answer back, right? The transition matrix will no longer change things because we've reached steady state. So that's sort of a curious idea. You have a transition matrix, you multiply it by a vector, and you get the same vector right back. It's a little bit odd, but if you think of it, we've reached steady state, so the transition matrix doesn't actually change the state anymore. We just get the same state back. If we rewrite this problem just a little bit, and if we think about the percent change we get when we get to steady state, so we lose 10% here, so negative 0.1, and we add 7% here, 0.07. On the other equation, we gain 10%, we lose 7%. And in steady state, there's no change. So we can set this equals to 0. And then we can see these are actually not independent equations. These are the same equation, just written 2 different ways. And so we can see x equals 0.7y, but we can't solve for what x and y are. We can only solve for the relationship between x and y. But we also have another piece of information we can use. So we know that x plus y equals 100 because we said there's 100 readers and we're assuming the readership stays constant. So then the steady state readership of the Big City Times will level out at 41.18%, and the Big City Herald will level out at 58.82%. All right, So we can make some new state vectors. So let's let our vector y equals v1, which was the readership in the first year, minus x, where x is the steady state readership of the Times and the steady state readership of the Herald. So then y is year 1 minus steady state, and here's our change. So minus 3.18 and positive 3.18. And now here's the interesting and very key part of the math. So we have our transition matrix P, and we multiply it by y. And what we get is this value negative 2.64 and positive 2.64. And if we look at this carefully, we can realize that this is 0.83 times y. So now we have an equation that goes as py equals scalar times y. And this form ends up being very important. But to finish out the newspaper readership question, we have year 2 is going to be p times v1, which is p times x plus y, which is x plus 0.83y. v3 would be p times v2 equals p times x plus 0.83y equals x plus oh, that's a typo, sorry, 0.83 squared y. And so we end up with a general equation. For year n, we're going to have x plus 0.83 to the n y. So we have a general equation now. And we got this general equation through this sort of unique properties of these matrices. So pay attention to this form, py equals 0.83y. That's an eigenvalue equation. So eigen is a German word meaning characteristic. An early, depends what you call early. When linear algebra and quantum mechanics were being formulated, a lot of science was done in German in those days. So eigen stuck as the characteristic word. So it's a characteristic vector and a characteristic value for this equation. And the general form is usually written as ax equals lambda x, where A is the transition matrix, x is a state vector, and lambda is a scalar. And here x is referred to as an eigenvector of A, and lambda is a scalar of A. So lambda is just a scalar, it's just a number. So if we have a transition matrix times a state vector, we get back that same state vector times some number. That's great, but it seems, how do we go about actually looking for eigenvectors and eigenvalues in some sort of systematic way, rather than just getting lucky or poking at numbers randomly for a long time? All right, so we'll look a little bit at how to systematically find eigenvectors and eigenvalues. Let's try another slightly silly problem, example math problem. So if we have the matrix A and we want to raise it to the 10th power times vector B, where A is this matrix 3, 1, 1, 3, and B is the vector 1, 2. Let's let X be a vector just XY. So we have our matrix, and we're going to multiply it times a vector. And this needs to equal lambda times that vector again. So we're looking for an eigenvector and the eigenvalues of this matrix A. So we have our matrix A, we multiply it by our unknown eigenvector. And this is going to equal lambda, our unknown eigenvalue, times that same eigenvector again. If we want to write it out in an algebraic equation, it ends up being 3x plus y equals lambda x, and x plus 3y equals lambda y. We can, of course, move the lambda and the x over to the other side. to put zeros on it. And then we can write a matrix of just the coefficients. So we have 3 minus lambda and 1. We have 1 and 3 minus lambda. So we write this in a matrix. And for x to be a non-zero vector, the determinant of the matrix C must be 0. So this is where that determinant property of matrices comes back in and is useful. So in this case, we need to solve the determinant and set it equal to 0. So we have 3 minus y squared minus 1, which ends up being just a quadratic equation, and lambda squared minus 6y plus 8, and the roots of that quadratic equation are 2 and 4. So the eigenvalues for this equation are 2 and 4. So if we plug this back in, we put it back in our eigenvalue. Lambda equals 2, 3 minus 2 is 1. We end up with x plus y equals 0, x plus y equals 0. And so an eigenvector, a possible eigenvector would be -1 and 1. And that would satisfy this equation. It would satisfy this eigenvalue. For lambda equals 4, 3 minus 4 is -1. So 3 minus 4 plus 1, 1 plus 3 minus 4, you end up with -x plus y, and x minus y equals 0. So an eigenvector of y is 1, 1. All right, but clearly those aren't unique. We'll come back to that point in a moment, but just to finish off this example, we can note that we can write B as a linear combination of our two eigenvectors. So we write B as a linear combination of the two eigenvectors. And since AX is equal to 2x and AY equals 4y, so here's our eigenvalue equation, just putting in the appropriate eigenvalues. We can expand this out and generate a general equation. So A times B is this long thing, A squared B, this long thing, A to the 10th is this long thing, but now we've just figured out what the general equation for it is. So we just put the 10th power here in front of 2 to the 10th and 4 to the 10th, and we get 1,572,352. That actual value is not important, but the important part is that we could solve this by having a linear superposition of the two eigenvectors. So coming back to that, eigenvectors aren't unique. So there's this indeterminacy of eigenvectors. Any non-zero multiple of x is also an eigenvector corresponding to the eigenvalue of lambda equals 2. Any non-zero multiple of y is an eigenvector corresponding to the eigenvalue of lambda equals 4. So we could have made an eigenvector of x prime with 2 and -2, or y prime is 1/3 and 1/3. And this, of course, will change the coefficients in the equation, but the final calculated result will be exactly the same. And the essential part of solving that was that we could take that vector B and express it as a linear combination of eigenvectors. And once we could do that, then we could turn the crank on the math and solve this. So expanding just a little bit more, for any given lambda, any given eigenvalue for an n by n matrix A, there's a set of eigenvectors x such that AX equals lambda x is a subspace of real numbers. And if we suppose that AX equals lambda x and AY equals lambda y, then for any scalars A and B, we could write A times AX plus B times BY. And we expand this out and then multiply it, we get lambda equals AX plus BY. So a non-zero linear combination of eigenvectors for lambda is still an eigenvector for lambda. So we can have a linear combination of these vectors, and it still is a solution to the system. All right. Thank you all for bearing with me. It will become relevant to physics and very shortly. All right. But we need one more level of abstraction before we switch back to talking about physics. The idea of operators and eigenfunctions are sort of one level of abstraction to eigenvectors. And so an operator operates on a function in a similar way that a function manipulates a variable. So we have our variable x, we can have our function e to the ax, so the function manipulates the variable x in a certain way, and then the operator will manipulate the function. So in this case, we have the operator, which is denoted by a little hat on top. So omega hat is the operator, and we can make it the first derivative. And we can make psi be a function e to the ax. And we can have these eigenfunctions with these operators. So omega hat psi equals lowercase omega psi, where lowercase omega is again an eigenvalue. So we've gone from eigenvectors to eigenfunctions, and it's just one level more of abstraction, but it's the same fundamental form. And so if we go ahead and solve with these example values, so omega hat psi is d dx e to the ax, which is equal to a e to the ax, which is equal to a psi. So we have our Eigenvalue equation. Psi is indeed an eigenfunction of omega, and the eigenvalue is a. All right. Finally, we have the tie-in to quantum mechanics and why you may care about all of this. If we go back and look at the Schrodinger equation, it can be written as h psi equals e psi. Well, that's interesting. We've seen this form before, right? We've seen this form of the equation before. So here, the wave function psi is an eigenfunction, and the energy E is the eigenvalue for H, which is the Hamiltonian operator. So all that building up with the silly newspaper example, we're getting to this form of the Schrodinger equation. The Hamiltonian operator just describes the total energy of the system. It's the kinetic energy plus the potential energy. And the wave function psi describes the state of the quantum system. So it's still that idea of we have an operator and it acts upon a state function, and we get back an eigenvalue and the state function. So it's sort of like the transition matrix in the state vector. It's just abstracted to an operator and a state function, which we usually call the wave function. And remember, we had the proof of the linear combination was still a solution. A linear combination of the eigenvectors was still a solution to the eigenvalue equation. Here, a linear combination of eigenfunctions psi is still an eigenfunction for E, which E is the eigenvalue for energy. And here's where the superposition of states comes out of the math. This is what bothered Schrodinger, and he made this paradox about the cat being alive and dead at the same time. How can you have a superposition of states? How can the system be in multiple states at once? And coming out of the math says, yes, a linear superposition, a linear combination of eigenfunctions is still a valid solution. So this was a case where theory-led experiment. The theorist looked at this and said, well, if we write this equation, it should work, but wait, there's this part that it predicts that doesn't make any sense. But then it's been proved experimentally that you can have superpositions of states, which is one of the reasons why quantum mechanics is so counterintuitive. but is one of the really powerful, useful properties of quantum mechanics that we're all trying to use to make quantum computers and things like that. So if we can generalize the eigenvalue equations a little bit, observables are properties of the system that we can actually measure. So I'm an experimentalist, I want to measure things. I want to measure the momentum or the electric dipole moment or something like that. And so the eigenvalue equation is we have some operator corresponding to the observable. We have our wave function. And then the eigenvalue is the observable times the wave function again. So the eigenvalue is what I can actually measure when I go into lab. That's why all this math is important, and that's what we can measure is this eigenvalue of the system. So if we think about a couple examples, let's say, look at the operator for linear momentum just in one dimension, so along the x-axis. So the operator px for linear momentum is h bar over I d dx. The operator for the x position is simple, it's just x. And if we try to use this operator technique and the eigenvalue equation, we can look for what the linear momentum is. And I'm going to call it psi right arrow, and you'll see why in a moment. And we'll take it, the wave function as a value a e to the I kx. So out of differential equations, if you take differential equations, you learn there's a series of solutions for different differential equation problem types. So we're just going to take that this is one of the potential solutions. So p hat of psi, right arrow, we have our operator, we plug in psi right arrow, which we've decided is a e to the I kx, or we're at least going to test a e to the I kx. We do the differential, we rearrange a little bit, and we find that we get k h bar psi. So we do have an eigenvalue equation. We have operator, wave function, constant, wave function. So the linear momentum in x would be, and if we measured it, we'd find it's k h bar. What if we chose the other solution? Say if we said b equals e to the minus I kx, we do it the same way, plugging in the wave function to our operator. This works out eventually as negative k h bar psi. And so the linear momentum here, if we measured it, it would be minus k h bar, because that's the eigenvalue to the eigenvalue equation. And I'm calling it to the left because traditionally we say movement to the left is negative, movement to the right is positive. All right. So if we think of a free particle, it's a little bit of a Gedanken experiment, but it makes the math a little more tractable for a lecture. A particle is flying along. We can write the kinetic energy as using the classical form. So p squared over 2m. Here we include the x subscript just to denote it's the momentum in the x direction. Then the kinetic energy eigenvector can be written out, and we get minus h bar squared over 2m d squared dx squared. And then we could write the Hamiltonian. So the Hamiltonian operator is going to be the kinetic energy operator plus the potential operator. For a free particle, we'll just set the potential equal to 0. And so then the Hamiltonian operator is minus h bar squared over 2m d squared dx squared. And this becomes the familiar Schrodinger equation for a free particle in one dimension. So minus h bar squared over 2m d squared psi over dx squared equals e psi. And solutions to a differential equation like this come in the form a e to the ikx plus b e to the minus ikx, where a and b are constants. So I did the two subproblems where we set a equal to 0 and where we set b equal to 0. But what happens to the linear momentum if we set a equal to b? So if we try this same operator and eigenvalue equation, we have our momentum operator, we put in our wave function, we do a transform from e to the ikx plus e to the I minus kx, which is also a description for cosine kx. These are equivalent. We do the derivative of a cosine, but we ended up with sine kx. We ended up with a different function at the end. So this is not an eigenvalue equation, because cosine kx is not equal to minus sine kx. This means we have an indefinite linear momentum, which is really hard to think about. What does that mean? But we can note that psi is a linear combination of psi right arrow and psi left arrow. So it's a linear combination of two eigenfunctions already. If we took a series of measurements, we could only get one value. We make a measurement, we get one discrete value. But we'd measure either kh bar or minus kh bar, and there would be equal probability of measuring both. So half the time we'd measure the particle going to the right, and half the time we'd measure the particle going to the left. That's because it exists in a linear superposition of these eigenfunction states, which is one of the really counterintuitive properties of quantum mechanics. In general, if we have a wave function that we know is a linear combination of eigenfunctions, we can have it as multiple. We don't have to have just two. We can have a higher degrees of superposition. We say these linear combinations are a superposition of these different states. And the C's are the numerical coefficients, and psi sub n's, the different quantum states. When we measure something, when we actually make a measurement and collect one of the observables, we're going to find the eigenvalue to just one of these psi's. We make a measurement, the instrument gives us an answer. It doesn't give us, here, you have 10 answers because you have a superposition. No, the wave function collapses and we get the eigenvalue of just one of these wave functions. And the probability of measuring that particular eigenvalue is proportional to Cn squared, where C is these numerical coefficients. So it doesn't have to be an equal superposition of states. It can be an unequal superposition of states. Just the probability of finding the particle in that particular state depends on what the coefficient is. So this is really the idea of where superpositions of states comes out of the math. And this is where the idea of collapsing the wave function comes out, because when we actually do the measurement, we only get one eigenvalue, and that eigenvalue is going to correspond to just a single wave function. It's not going to correspond to the whole superposition of wave functions. So if we just go back, I'm an experimentalist, so I have to go back to the lab to wrap up. If we go back to this double slit diffraction problem that we were looking at last week, it works with photons, it works with electrons, it works with fullerenes. When we send something to this double slit, which slit it goes through ends up being a superposition. So it effectively goes through both, and we get the diffraction pattern, even if we slow this down so one particle at a time goes. If we try to make a measurement, if we put the detector right behind one slit, or we put the detectors right behind both slits and don't give the wave function time to evolve, we'll get the answer that it either went through this slit or it went through the other slit. We're never going to get send one particle in and we're going to have detectors right behind both slits and we're going to get both detectors going off at the same time, it will always go one, the other, one, the other. But if we allow the system to be in this linear superposition, the linear superposition wave functions can actually interact with each other and we get this diffraction pattern that builds up. All right. So in conclusions, sometimes the theory leads to the experiments, sometimes the experiments lead to theory. This idea of superposition of states in quantum mechanics, it was the theory that led the experiments, and the theory sounded so crazy, even the person who came up with the theory said, this is crazy, you can't have a cat that's dead and alive. But the superposition of quantum states is fundamental to quantum systems and it's fundamental to quantum computing. And linear algebra really provides the framework for eigenvalue equations and how to handle them. And hopefully, maybe if you go back through the talk a couple times, you can start to get your head wrapped around exactly how this all comes out. And when we go into lab, and I'm a lab rat at heart, what we actually measure are the eigenvalues of these equations. So that's, we need to know what we think we're going to measure, and then what we think we're going to measure are going to be the eigenvalues for these equations. So I went back to my old textbooks, which were these, and used them for reference and pulled examples for this talk out of these textbooks. Several of them have been updated quite a number of times in the intervening 20 years. So these are old editions. You could either look for newer editions if you wanted, or these old editions. Quantum mechanics hasn't changed that much in the last 20 years. Linear algebra hasn't changed in 20 years. So you can still use these and you can find them cheaply on the internet for like $5. With that, I'm happy to answer questions and go back and go over anything that was confusing.
I don't have any questions. I have to chew on some of this stuff. Taking me back quite a bit. But very well done. I wish, you were there to explain it. I won't say how many years ago. But
yeah, so certainly it's a large topic to try to cover all in a small amount of time. It's trying to put like 3 semesters of work into a small, but hopefully it was logical enough building up that the students can go back and chew on it a little bit. I'm happy to have discussions and questions after you've had time to chew on it a little bit.
Let's see what's in, that's great. Let me see what's in the chat. Oh, that was Carolyn. She said excellent. Okay. Don't be shy, folks. Or you just want to save your questions for next time?
Next time will be experimental. The indeterminacy of eigenvectors again. Yes, we can do that. Let me go back to my slides.
Oh, someone asked a question?
Yeah, someone asked a question if I could go over the indeterminacy of eigenvectors again.
Oh, okay.
So, all right, so it really comes out of here. So the eigenvalue is set. The eigenvalue is 2, or the eigenvalue is 4. When we have this matrix as the coefficient matrix for solving the eigenvalue equation, it has to equal 0. The determinant of this matrix has to equal 0. So then we end up with a quadratic solution, a quadratic equation, and so the quadratic equation has certain roots. The quadratic equation comes out with the lambda equals 2 or lambda equals 4. Those are the roots of the quadratic equation. When we plug those roots, those values for lambda back into these eigenvalue equations, we get x plus y equals 0. Well, we get it twice, which is not that interesting. We get the same equation twice when we just plug this lambda equals 2 back into here. And one solution would be for x equal to be -1 and y equals to 1, right? -1 plus 1 is 0, -1 plus 1 is 0. But that's not the only solution, right? You could have 2 and -1, so 2 plus -2. You can have 2 and -2. 2 plus -2 equals 0, right? So you can have a bunch of different eigenvectors that all correspond to this eigenvalue. So this is where the eigenvector is not unique, and there's a lot of indeterminacy to it. So for this example, I picked -1 and 1 and 1 and 1 just for sort of nice clarity, sort of the simplest eigenvectors you can think of. But as I say 2 slides later, you could have 1/3 and 1/3. And anything where x equals y and anything where x and y have opposite signs and are equal will be eigenvector solutions to this. So there's sort of an infinite number of eigenvector solutions to this problem. And this is the indeterminacy of it. It's not a unique solution. There are many solutions to this eigenvalue. So in quantum mechanics, we can have different wave functions that still correspond to the same energy if we're doing Schrodinger's equation. Did that help? Sorry, let me see if I can find the chat again.
Yeah, she said that helps.
Okay.
Yeah.
That's good.
Okay. Okay, with that, I think we'll call it a day. And this is, I can't explain how well this is really connecting with how the classes are sort of really helping each other out. Because we're taking, I don't know if you saw that, the vector calculus for E&M. And he's going over so he of course talked about dot product and scalars and all, and what a vector was, what a vector is. But he kind of, some of the things that you highlighted, like how to add them and transpose them and stuff like that, he didn't really discuss. So it's almost like you had to, if you didn't know that, people know it, but they may not recall it. So it's like the two are kind of working each other out. And then he's talking about Cartesian coordinates. And frankly, the diagram that you showed, that's classic, but he gave a problem set based upon that. So you actually just gave everyone a big hint on how to do it. Which, yeah, it's working out. It's really working.
That's good.
Yeah.
That's good, especially since I'm not paying any attention to what the other classes are doing. I'm glad they're all syncing up.
Yeah, it's really, I couldn't have, it's like, I'm giving myself a pat on the back, but I didn't really plan it this well. It's all kind of working out. Okay, this part will have to be taken out of the recording. Anyway, thanks so much. I'll see you next week. And we'll talk about the fall.
Okay.
Okay. All right. Thanks, Arthur.
Have
See
a
you
good
later.
one.
You too. Stop recording.